You know when you type something on your keyboard, how does it just work? How does it show up on a screen halfway across the world looking exactly the same? Well, there's this incredible hidden system that makes it all possible. Today, we're going to pull back the curtain on that system and talk about what happens when it goes spectacularly wrong.
Okay, so let's dive right in. And we're going to start with a problem that I can almost guarantee you've run into, even if you had no idea what to call it. Picture this. You're browsing a website, maybe digging through an old forum, or you open up some text file. And instead of actual words, you just get, well, you get this.
So yeah, that complete mess of symbols, it actually has a name. It's called mojibake. And the crazy thing is, it's not random at all. It's a sign, a symptom, that a computer is trying to read a message using the wrong dictionary. And to really get what that means, we've got to understand how these dictionaries are made in the first place. All right, here's the absolute key to this whole thing. Computers, they don't actually understand letters, or emojis, or even a period. They only get one thing, numbers. That's it. So character encoding, think of it like the ultimate master key, or a secret decoder ring. It's the system that translates every single character we use into a number that a computer can finally understand.
Okay, so to figure out how we eventually fix this mess, we have to rewind. Let's go all the way back to the beginning, to the very first major attempt to create a standard for all of this, at least for the English language.
You know, long before we even had computers, we were trying to solve this problem, turning letters into signals. You had Morse code with its dots and dashes, right? Then the baud code for telegraphs, which used a 5-bit system. But the real game changer, the one that set the stage for the digital age, dropped in 1963, and its name was ASCII.
So ASCII's whole deal was being super simple and straightforward. Look here. When a computer stores the word code, it's not actually storing letters. Nope, it's storing a sequence of numbers. 67 for C, 79 for O, you get the idea. Every single letter, number, and symbol in English got its own unique ID number.
And honestly, it was brilliant, so compact. It used just 7 bits of data. Now, a bit is just like a tiny on or off switch, so with 7 of them, you get 128 possible combos. This was perfect back then when computer memory was super precious. But its greatest strength was also its biggest, most fatal flaw. It was the American standard code. And, well, the rest of the world uses a lot more letters than just the English alphabet.
And this focus on just English, it was about to cause a massive problem, a truly global one. You could almost call it a digital Tower of Babel.
So, because ASCII only really worked for English, everybody else had to make up their own system. And all of a sudden, you didn't have one standard, you had hundreds. Seriously, each region, every language, even different operating systems had their own special way to map their characters to numbers. It was, in a word, chaos.
Now you might be thinking, well, why didn't they just make a bigger code that fits everyone? And that's a great question, but you have to remember, back in the 80s, computer memory and storage were insanely expensive. The idea of adding even one extra bit for every single character, just to support languages you might never even see, that was considered a huge waste. The name of the game was making every single bit count.
And this right here, this shows you the problem perfectly. Imagine a computer gets the number 224. Okay, what does it do? Well, if it's using the dictionary for Western Europe, it shows an A. But if it's using a Russian dictionary, it shows the Cyrillic letter P. It's the exact same number, but with 2 totally different meanings. See the problem?
So clearly, the world was desperate for a single universal system. We needed a master plan, something that could handle every character from every language, both past and present. And that system is called Unicode.
And this is where the big, revolutionary idea comes in, the one that changed everything. You see, all the old systems tied a character directly to a specific set of bits. Unicode's creators basically said, wait a minute, let's break that chain. Their idea? First, let's just give every single character a permanent, unique ID number. Then, and only then, we'll worry about the best way to actually store that number. It works in these 3 really elegant layers. So first, you've got the repertoire. Just think of it as a massive list of every character you could ever imagine. Then, layer 2. Every character on that list gets its own permanent, unique number. We call that a code point. So the letter A is always U plus 0041. The thumbs up emoji, it's always U plus 1F44D, forever. And finally, you get to the 3rd layer, the encoding. That's just the rule for how to turn those code points into the actual bytes that get saved on a computer. So if Unicode is the grand architecture, right, the big blueprint for world peace in the world of text, then one specific encoding scheme became the hero that actually made it all happen, the one that brought this plan to life for the entire internet. And this number, well, this number really says it all. As I'm recording this, almost 99%, I mean, think about that, 99% of all websites use UTF-8. It is the undisputed champion, the standard for text on the web. So the big question is, how did it win so completely?
Well, its huge success really boils down to three brilliant design choices. First, its variable width. What's that mean? For simple English text, it only uses 1 tiny byte per character. But for any other character in the entire world, it can expand and use up to 4 bytes. This makes it crazy efficient, right? No wasted space for the most common stuff. And here's maybe the most clever part. It's perfectly backwards compatible. The first 128 characters are exactly the same as old-school ASCII. This is a genius move because it meant old systems could still read it without completely freaking out, making the switchover super smooth.
And check this out. This shows that efficiency in action. To store this string with all its special characters, UTF-8 only needs 9 bytes of space. But other ways of encoding Unicode, like UTF-16 or UTF-32, they're not as flexible. They take up way more room. For the web, where speed and efficiency are everything, it was no contest. UTF-8 was the clear winner.
All right, so let's bring this all back. What does this whole technical story about bits and bytes and codes actually mean for you, in your daily life?
Remember that garbled text from the beginning, the moji bake? The reason you hardly ever see that anymore is because pretty much the entire world agreed to use one universal dictionary, and that dictionary is Unicode, brought to life by UTF-8. There's no more guessing game, no more trying to figure out which decoder ring to use.
This system, it's the invisible foundation of our global internet. It's the reason you can type an email that mixes English with, say, Greek and Japanese. It's why you can just text someone a simple thumbs up emoji and know for a fact that they're going to see a thumbs up, not some random symbol.
At the end of the day, it's just a perfect example of how agreeing on one smart, elegant standard can solve a problem that seemed, for a while there, impossibly complex. It's this hidden triumph of engineering and, really, cooperation that we all get to benefit from, literally every minute of every day.
And that kind of leads to a final, much bigger question, doesn't it? We managed to standardize something as fundamental and as incredibly diverse as human language. So, what other huge, complex global problems could we solve if we applied that same kind of thinking? I'll just leave that with you to think about. Thanks so much for tuning in to this explainer.